Greetings from Vignesh. So this was our assumptions which were made for the following assignment. The net force acting on the body was assumed to be 0. Since it's a constant velocity problem, the v is equal to cdv by dt is 0, which is actually the acceleration. So the force acting on the body also becomes 0 since a is 0. Applying Newton's second law, final velocity is equal to initial velocity plus net force divided by mass into delta t, and also the final position is equal to initial position plus final velocity into delta t, which is actually the change in displacement. The case assumed here was the rolling ring, whose mass was found to be about 0.42 kgs and width was found to be 0.035 meters, which was used for calibration. So this is actually the video of the ring running across the screen. Then this is the tracker file which was used. This shows the frame rate, total length, and this shows the path traced by the ring, and also the graph and the points, coordinate points extracted from the tracker software. So knowing the width of the ring, the blue line which shows the calibration, it was quite easy by measuring the width of the ring. The calibration was done. Observation and calculation. The mass of the ring was found to be 0.42 kgs. The total time of travel of the ring was found to be 3.98 seconds. Average velocity is equal to change in velocity by change in time. It was applied, and the initial velocity, final velocity, and the total time taken was given to find out the total average velocity of the ring. This shows the vectorial representation. This is the Python program. The ball mass was given. The initial position of the ball was given as 0, 0, 0. The initial ball velocity was given, which was done in the earlier calculation. The delay time was given as 0.07 seconds. The while loop was constructed, from which the net force, ball velocity, and ball positions were extracted. So this is running the module. You get something like this of uniform velocity. Actually, the process speed was very slow. I decided to go for Excel graphs. So this shows the model graph along a comparison with the experimental graph, which shows the experimental points were less scattered and was almost close to the model position, with minimal error. So what if the choice of the axis was changed? So editing the Python program, to change the axis, the negative sign was removed and it was replaced by a positive sign, and the graph and the model was run. So as expected, the ball was moving towards the right, which was earlier in the left. So the coordinate points were the points were extracted into an Excel file, and the graph was drawn, which was a straight line in the first quadrant, whereas the earlier one was in the fourth quadrant. It shows the change of direction, the velocity vector. So the next thing was, what does it mean? So setting the net force not equal to 0, which was 0 in the previous case. So if the net force is not equal to 0, then what happens? So to edit the Python program, the net force was initially 0, so changing it to be 2 in x and 3 in y direction. Running the module, you get a fast ball running, something like this. So from which the coordinate points were recorded, and Excel graphs were drawn, and this shows a parabolic curve in which the displacement increases non-linearly with the increase in time. So conclusion, from the constant velocity graph, the graph was a straight line graph between the displacement and time, which shows a constant slope. So constant velocity, which is change in displacement with change in time. So from the what graph, displacement direction changes, which shows the orientation of the axis changes, the displacement also direction changes. So what does it mean? A graph was parabolic, increasing slope, so increasing velocity, which was the presence of acceleration, and the net force was not equal to 0, which was the initial conditions. So thank you.